So, welcome back to lectures on engineering mathematics 2. So, this is lecture number 53 on inverse Fourier transform. So, in this lecture we will be talking about the inverse Fourier transform and some of its property like linearity etc. So, we will also discuss the uniqueness theorem, which has to be discussed now in case of the inverse Laplace transform, because inverse Laplace transform is not unique, and then some worked problems will be demonstrated for inverse Laplace transform. So, coming to the existence of Laplace transform, which was the last lecture, we need a function which is piecewise continuous and of exponential order, and these two conditions were sufficient to for the existence of Laplace transform. So, the idea was we have the Laplace transform e power minus s t f t dt, and if we just break into two parts 0 to t naught and then t naught is some finite number t naught to infinity e power minus s t f t dt. So, the idea was for the existence of Laplace transform that this piecewise continuity takes care for the existence of this portion where we have the limits finite, and for this portion when we have t naught to infinity, then this exponential order, the functions of exponential order takes care for the existence, and as a whole we discussed that these two conditions are actually sufficient conditions for the existence of Laplace transform, but they are not necessary, and we have shown some examples where the functions were not piecewise continuous and then the Laplace transform exists. Also the function was not of exponential order, but still the Laplace transform exists. Now, we will come to the inverse Laplace transform, and the idea is simple, that if we have for instance this f s is the Laplace transform of f t for some function this f t, then we define the inverse Laplace transform as the Laplace inverse transform of this f s is equal to f t. If we know that the f s is the Laplace transform of f t, then the L inverse, the Laplace inverse of f s will be f t. So, that is the simple inversion. For instance, if we know that the Laplace transform of sin w t is w over s square plus this w square. In that case, we can say that the L inverse of w over this s square plus w square is equal to sin w t for t positive. But there is a problem here. For instance, if we consider the function g t, we define as that t is equal to 1, the value is 1, and otherwise it is sin t. So, at t is equal to 1, it is not sin 1, but we have defined a different value as 1, and other than this t is equal to 1, we have sin t. Actually, we can define many such finite points where the value differ for this function g t, and otherwise it is sin t. So, if we take the Laplace transform of this g t, which is defined here as t equal to 1 and otherwise sin t, in that case we will end up with 1 over s square plus 1, and it is clear because the integral which is 0 to infinity e power minus s t and for instance this g t dt, it does not read the value at discrete points. So, eventually this is the Laplace transform of sin t only. So, we will get here the Laplace transform of this g t the same as the Laplace transform of sin t. Now, having the earlier definition which we have given, that if the Laplace transform of sin t for example is s square 1 over s square plus 1, then the L inverse of this 1 over s square plus 1 will be sin t. But here the problem is, now we have a g t function which is actually different than sin t. So, the Laplace transform of this 1 over 1 plus s square, whether we should say it is sin t or we should say it is g t, or we can define several other functions whose Laplace transform will be 1 over s square plus 1. So, in that sense the inverse Laplace is not unique, because we have the Laplace inverse of 1 over s square plus 1 as sin t, we have also the Laplace inverse of 1 over 1 plus s square as g t. So, there is a theorem here, the nice result by this Latz theorem. If f and g are continuous and are of exponential order, and then if we have this f s is equal to g s, if the Laplace transforms are equal for this s greater than s naught, then f t would be also equal to g t for all t. So, at least we have this uniqueness when we are talking about the continuous functions. So, if f and g are continuous and their Laplace transform is same, then we can say that actually these functions are same, that Laplace transform cannot be the functions cannot be different if their Laplace transform is same. But this is only true when we are talking about the continuous function. So, let us first go through this theorem and then we will have a little more discussion on this uniqueness part. So, just we will present here outline of the proof. So, suppose this f s is equal to g s for all s greater than 0. In that case, we have these two integrals equal, because this is the Laplace transform of this f t and here we have the Laplace transform of g t, which are denoted by f s and g s respectively. So, having this equality, we can bring everything to the left hand side. Then we have the integral e power minus s t f t minus g t and integrated over t from 0 to infinity, and that is equal to 0 for all s greater than s naught. Having this, now we have a nice result which we will prove in the next slide, which says that if we have this 0 to infinity e power minus s t h t d t equal to 0, this implies that h t equal to 0, but we need to prove this result. Let us first use this result and prove this Latz theorem. Later on we will show that indeed this is the case. When we have e power minus s t h t d t equal to 0, this will imply that h t equal to 0. So, here having this result with us, we have e power minus s t and there is a function here f t minus g t d t equal to 0, and this holds actually when this h t is continuous. So, in this case also we have this continuity because f and g are continuous. So, in that case we can say that f t minus g t is identically 0 for all t, that means this f t equal to g t for all t. So, this is the outline of the proof, but we have to show that e power minus s t h t d t equal to 0 implies that h t equal to 0. So, to prove this result, we will consider here this lemma, and using this lemma we can show that this result holds. So, here this lemma says if h t is continuous on this 0 to 1 in this interval 0 to 1, and when we have this integral now 0 to 1 h t t power n d t equal to 0 for all this n 0 1 2 3 and so on, that implies that h t equal to 0. So, first we will prove this lemma, and with the help of this lemma we will get back to this result. So, since here the h t is assumed to be continuous, so h t is continuous function, then we can find a polynomial p epsilon such that h t minus p epsilon is less than equal to epsilon. So, this is the result which we call the Weierstrass approximation theorem, and it says that if we have this continuous function defined on this closed interval like here 0 to 1, then we can find a polynomial of as good accuracy as we want. So, we can basically approximate a given continuous function by the polynomial, and the accuracy we can set here as written here epsilon. So, for any epsilon we can find the function the polynomial p epsilon which actually the difference from this function is less than the epsilon. So, this is so called the Weierstrass approximation theorem, and using this now we will move further. So, we have this information that 0 to 1 h t t power n dt is 0 for all n 0 1 2 3 and so on. So, having this in result now, what we can say that 0 to 1 h t, this p epsilon t dt will also be 0, because this is a polynomial and the polynomial will have some form of like a 0, then x n, then a 1 x power n minus 1, or t, rather we are talking about t here, the t n minus 1 and so on. And then individually we know that this h t t power n is 0. So, we have basically here t power n minus 1 and so on. So, this polynomial by this result, because for any value of n this is 0, then here we are keeping the polynomial, and polynomial will have this linear combinations of such terms t power n. So, definitely then this integral will be also 0. So, having this integral equal to 0, what we can now say, if we take the limit epsilon goes to 0. So, having this having said that epsilon goes to 0, meaning that this p epsilon, the polynomial which we are taking for the approximation of the function h t, it will become actually h t, it will go very close to h t as we take the smaller value of epsilon. So, in the limiting case, when epsilon goes to 0, this polynomial goes exactly to this h t, it will meet with this graph of h t. That means, in the limiting case here, when epsilon goes to 0, we have h t, and this polynomial will also will converge to h t. That is the Weierstrass theorem. We have seen that this polynomial epsilon goes to, when epsilon goes to 0, this actually goes to this continuous function. So, we have this h t square dt, and which means we have this positive or h t square in the integrand, and that will imply that this has to be identically 0 to have this integral equal to 0. So, what we now need to prove that when we have e power minus h t dt equal to 0 for all s this greater than alpha, then this implies that h t equal to 0, that we will prove now. So, we will use indeed this result, that means h t t power n dt equal to 0 implies h t equal to 0. So, here we will fix this s, we will take s naught which is greater than this alpha. So, this integral will be valid for all these s, and now we substitute u equal to e power t, that means we have ln u is equal to minus t, or we have basically du also minus e power minus t dt, and then so du and e power minus t is u. So, this du can be replaced by this minus u dt. So, having this, and we will take this s as s naught plus this n plus 1. So, here we are introducing n, we are going into this direction now. So, here this result says that 0 equal to this 0 to 1, then the limits here which was 0 to infinity, when we had this t 0, this will go to 1, and when t is infinity, this will go to 0. So, we have this result, and this minus sign will be adjusted to reverse the order of the integration. So, then we have here e power minus s t and this e power minus t. So, this will be written in terms of this u, then h and t is this minus ln u, and then we have this du, and there will be a factor u over u power s naught when we substitute this in this. So, we have this u e power minus t. So, when we substitute this e power minus t, this will be u power this s, u power this s, and then we have h and t is minus ln u in the integrand, and this du. So, one u will be there which is coming from this du. So, because the du will be e power minus t dt, and then this implies that du is equal to minus sign with u and dt. So, this when we replace this dt, there will be a u term there. So, 1 over u, but when we are keeping this u power n and n is taken as s naught plus n plus 1. So, this 1 power will be cancelled out with this u, and then we have u power n and then u power s naught. So, having this now, this integral which is just after substitution we can get. Now, if we look at this form here, we have u power n similar to what we have there t power n, and then we have some function here, some continuous function sitting, and then we have this du which was dt there naturally. So, if this result implies this h t equal to 0, identically here also we are getting the same result. That means, this u power s naught and the h, the function of this minus ln u, will be equal to 0. So, we got and this is naturally here ln u is just a t there, minus ln u is nothing but t. So, this h t and this u power s naught, u power s naught is not 0, u power s naught is not equal to 0, because u varies from this 0 to 1 and s naught is also a number here greater than this alpha. So, this cannot be 0, only possibility is that this h t, this has to be 0 now to make that integral 0. So, that is what we have proved now, that e power minus h t dt equal to 0 implies that h t equal to 0. So, we have this now some remarks. The uniqueness theorem holds for piecewise continuous function as well, but there will be a difference, that for piecewise continuous functions means that the function is continuous except perhaps at discrete set of points where it has kind of jump discontinuities, like this Heaviside function we have seen. So, since this Laplace integral does not read the values at the discontinuities. So, in this case what we have, in this case means the case when we have the piecewise continuous function. So, in this case we can only conclude that f t will be equal to g t outside the point of discontinuities. So, what the result can be also proved formally, though we understood this intuitively, that when we have two Laplace transforms equal, then the functions whose Laplace are these functions, those functions will be equal other than or outside the points of discontinuity. Well, so let us go through some problems based on the inverse Laplace transform. So, if you want to find the inverse Laplace transform, for instance, of this function, which is 6 over 2 s minus 3 and 8 minus 6 x divided by 16 s square plus 9. So, looking at the structure here of this Laplace transform, it seems that here we can have some kind of the exponential function, and then here we have this s square plus something. So, cosine or sine type of functions. So, if we take this Laplace, we can use the linearity property, that means this f t taking the inverse Laplace transform both the sides. We have the Laplace of 1 over 2 s minus 3, then here Laplace inverse of 1 over 16 s square, and then Laplace inverse of s over 16 s square plus 9. So, what we will do now, in the first case we will take this common, so that we have s minus a form. So, taking this common here 2, that means we have now 3 there, L inverse 1 over s minus 3 by 2. In this case we will take this 16 outside this bracket. So, we have 1 by 2 and then L inverse 1 over s square plus this 9 by 16, and in the third case we will take this 16 out. So, we have 3 by 8 and L inverse s over s square plus this 9 over 16. So, we have now the structure which we know from the basic functions, that whose Laplace transform is 1 over s minus a, whose Laplace transform is this s square plus a square form, and s over s square plus a square form. So, having that knowledge, we can say now we can conclude that 3, this is the Laplace transform of e power 3 by 2 t. So, 1 over s minus a, the Laplace inverse, it is e power a t. So, we are writing here e power, this a was 3 t by 2, and then in the second case we have here 3 by 4. So, we have the situation that s square plus 3 by 4 whole square. So, we need 3 by 4 also there to have this sine function, that means 4 by 3 we have to multiply, and 1 by 2 was already sitting there. So, that is a 2 by 3 now. So, here we have 2 by 3 and then sine of 3 t by, because 3 by 4 is there. So, 3 by 4 t. So, we are done with this term also. Here concerning this one we have direct result, because s over s square plus a square, and the a square is this 9 by 16, that means a is 3 by 4 again. So, this L inverse of this, that is cos a t. So, we have 3 by 8 and L inverse 3 by 4 t. So, that is the function whose Laplace transform is given as this 6 over 2 s minus 3 and 8 minus 6 x over 16 s square plus 9. The second problem, we will consider the inverse Laplace transform of this function, which is f s is equal to 3 s square minus 28, then we have s minus 4 and then we have s square plus 4. So, in this case what we have to do, and that is one trick which we always, I mean most of the time it works, it is the partial fraction, the decomposition to the partial fractions, because we have this s minus 4 and s square plus 4. So, if we can decompose using this the idea of partial fractions, then we will get something of this 1 by 4 and then here s square plus 4, and then we can convert into the known functions, the Laplace transform of known functions, then we can get back to the original function. So, using this partial fraction decomposition, what we have, that this can be written now a over this s minus 4, this factor, and then here we have this quadratic term s square plus 4. So, there will be a linear term there b s plus c. So, a, b, c are constant which have to be evaluated, so that this relation holds. Once we are done with the calculation of these a, b and c, we can just apply the inverse Laplace both the sides and we can get the desired result. Okay, so, going to these partial fractions, we have this 3 s square minus 28. So, here also we make this denominator equal. So, then in the numerator what we will get, we have a s square and then will be b s square term. So, with s square we will have a plus b, with the s we will have here minus 4 s, and there will be c s. So, c minus 4 b s, that is the term with s, and the third one we have the constant term. So, there will be 4 a and minus 4 c. So, 4 a minus 4 c. So, we have now the numerator here which has to be equal to the left hand side, which is 3 s square minus 28. So, we can compare here, because here 3 s square and the coefficient of s is 0 left hand side, and then minus we have 28, the right hand side we have a plus b s square, then we have c minus 4 b s, and then we have this constant term 4 into a minus c. So, by comparing this we realize that this a plus b is equal to 3, and here c minus 4 b is equal to 0, and this a minus c is equal to minus 28, or from here we can say that this a minus c is equal to minus 7, and then here we have this result that the c is equal to 4 b. So, we can substitute here indeed 1 minus this 4 b is equal to minus 7. This is one equation in a b, and then we have the other equation in a b as a plus b is equal to 3. So, solving these equations, what we get now, so if we subtract this, the a will get cancelled and we have minus 5 b is equal to minus 10. So, here we will get as b is equal to 2. So, B is 2, then C is 8, and then from here we can get, if this B is 2, then A has to be 1. So, we have A 1, then B 2 and C 8, A 1, B 2 and C 8, and this was the idea of the partial fraction, that A over S minus 4. Here we have B S plus C by S square plus 4. So, having this equal to, now we have A, so 1 over S minus 4, then the B is 2, so 2 S plus 8 by 4, and now we are done. So, the main work here is to get these partial fractions. Once we have done the partial fractions, it is just a matter of inverting, because we know now whose Laplace transform is 1 over S minus 4, and here also we can further write 2 S over S square plus 4 and then 8 over S square plus 4. So, now we can get the Laplace inverse, that means the Laplace inverse of 1 over S minus 4, Laplace inverse of S over S square plus 4, and Laplace inverse here 4 into 2. So, here we have 4, L inverse 2 over S square plus 4. So, we have the direct results now, that e power 4 t will be the function whose Laplace transform was 1 over S minus 4. Here S over S square plus 4, again known function, that is cos 2 t. Here we have 2 over S square plus 4. So, we have sin 2 t. So, this e power 4 t, 2 cos t and plus 4 sin 2 t, that is the Laplace inverse of this given function. Now, we want to find the Laplace inverse of this function S square plus S plus 1 over S cube plus S. Now, the idea is same as I said before, that we have to do this partial fractions. Once the partial fractions are done, we can simply use the existing result to get the functions back to the t domain. So, we have the partial fractions decomposition now again, because here we have this S and S square plus 1. So, we can write down then A over S, and for S square plus 1 again this B S plus C will come. So, here this S is S into S square plus 1, and then numerator will be A plus B S square plus C S is equal to A. So, again we get the equations here, that A plus B is equal to 1, then C 1 and A 1, and once A is 1, then B is 0 from the first equation. So, having this, now we have 1 over S, because A was 1 and the B is 0. So, this there will be no S term, C is 1. So, we have 1 over 1 plus S square. So, it is a much very simple fractions we got here, whose transform we know already. L inverse 1 over S is 1, and the L inverse of 1 over S square plus 1 will be sin t. So, we have the result here, that this inverse Laplace transform of this S square plus S plus 1 over S is cube plus S is 1 plus sin t. We want to find now the Laplace transform of this function. So, S square minus S plus 2, where S square minus 3 S minus 10. So, here also we have to just do the fractions. So, here S, and this is S minus, so we can have here, so S minus 5 and S plus 2. So, this is the product of S minus 5 and S plus 2. We can factorize that, and again we have to go for the partial fractions, that means A over this S plus A over S plus 2. So, we have here A over S, then B will be over S minus 5, and then C will be over this S plus 2. So, by doing this partial fractions, we will observe that this A factor is coming as minus 1 by 5, then the B with S minus 5 here it is coming 22 by 35, and with this S plus 2 the C is coming as 4 by 7, and then we can apply the idea of the inverse transform. So, we get here 1 minus 1 by 5 and this is 1 only, then s minus 5 will give e power 5 t and here we will get e power minus 2 t. The last problem where we will get this inverse transform of this, and here now we have s square plus 4 and s square plus 1. Again we need to go for the partial fractions, but this time we will have here also this linear term, there also linear term a s plus b and c s plus d. So, in this case we have to compute these 4 coefficients a, b, c, d. So, it could be difficult sometimes to get these partial fractions, but that we have to do to get this inverse, because directly we do not know how to get it. So, we do the fractions into the non inverse transform, the non Laplace transform, and then we will take the inverse Laplace transform. So, here this after doing the partial fractions, it comes out to be that 7 by 3 is with s here over s square plus 1, and then this 1 over s square plus 1 for this b, that is b is 1, and here the d is coming to be 0 and the c is coming as minus 1 by 3. And then we can go for the inverse transform, because this is just for cos t, this is for sin t, and then here we have cos 2 t. So, using the idea of these partial fractions, we can easily compute the inverse of some complicated expressions by doing these partial fractions. So, these are the references we have used for preparing this lecture, and just to conclude, we have discussed the uniqueness theorem for inverse Laplace transform. So, which says that if f s is equal to g s for all this s greater than s naught, in that case at least this f t is equal to g t outside the points of discontinuities. And the evaluation of the inverse Fourier inverse Laplace transform is done based on this idea of the partial fractions. So, this is one of the techniques to get the inverse of the Laplace transform. Well, so that is all for this lecture, and I thank you for your attention.